All right. So let me first summarize again what happened last time. There are several things. The one thing which was important, which was a parallel to Tim's lecture, was that I got in my pedestrian way polarization vectors for gauge bosons, and actually that's exactly the same that Tim got in a different way. So it's, well, okay, it's your call, whichever way you prefer. Okay. Mine was very pedestrian because I was essentially doing boosts and performing Lorentz transformations and some trivial solutions, okay? So in that case, you get exactly the same thing, that the plus polarization vector was written in terms of the momentum spinors. Okay, so lambda is the momentum spinor corresponding to momentum k, and then r is arbitrary reference spinor. This is exactly the same thing that Tim got. So again, you see that actually in his notation, when you go to represent this polarization vector as a matrix, is simply that. Yes, so it's exactly the same. The y, of course, that is, of course, is the denominator, but this is what you get. All right? So it's exactly the same thing. And then one thing which I told you, that this reference spinor, which actually defines also a reference vector by taking r and r bar, is the choice of this reference spinor, reference vector, is, as you will see, simplifies many computations. And also this representation is very useful to seeing explicit that they are dealing with helicity plus one, yes? Because essentially you have a helicity plus 1/2 from here, and this is plus 1/2 from here. So that actually makes explicit the little group transformation properties, okay? And then there was one formula which I derive, and I will keep it because I'll be using today, is that if you take a scalar product of this polarization vector with arbitrary, again, light-like momentum vector, so we'll get this type of object, which I'll be using often. Okay. Lambda now is denoted, of course, by k. It's momentum spinor corresponding to k. And then if I take a scalar product of that for negative helicity, I get the same thing, just when replacing angles by squares. Okay? All right. I will keep that now because I'll use it later. Okay, and then the one thing which I told you that, again, I discussed the consequences of the little group transformations, Lorentz transformations, which leave for a given momentum is the group that leaves the momentum invariant and consists of 3 group elements. One of which, of course, the rotation about the direction of motion. And then there are 2 other combinations of boosts and rotations. And altogether, I mentioned that this group, okay, at the end, if you look at the algebra, of little group, is the group of Euclidean, of the symmetries of Euclidean plane, of 2-dimensional Euclidean plane, which means it's rotations and 2 translations, yes? All right. And then I use these symmetry transformations under little group, and the fact, and first I will use the symmetry transformation under little group to write, to consider 3-point scattering amplitudes. For that I chose complex momentum conservation in order to get something non-trivial, okay? And then, so I consider the case of helicities which are plus minus 1, and I consider a possible configuration plus, 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 minus, 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 and so on. And I told you that only one amplitude, sort of, that in a theory with a dimensionless coupling, which is Yang-Mills theory, only one amplitude makes sense, and the amplitude which has two minuses and one plus. Again, this is assuming that I'm working with a holomorphic solution of the momentum conservation constraints. Okay? Now, and that amplitude turned out to be, I just want to see how I wrote it. I wrote it in the following way. This is 1, 2, 3. So 1, 2, cube divided by 2, 3, 3, 1, times something, okay, that I got. This is just for what I can get from those just dimensionful and little group arguments. And it's indeed satisfies all constraint, including the fact that this has dimension 1, so I don't need any dimensional coupling. Okay, so this is exactly the only amplitude that makes sense in a theory with gauge bosons. But now you see that this, I told you also that if you interchange 1 and 2, then the amplitude should be symmetric, yes? But this one is anti-symmetric, which means that if you have abelian theory, okay, that this has to be 0, so it has to be 0 and QED, and both 3-photon amplitude must be 0. Okay, however, in Yang-Mills theory, well, I can distinguish between 3 gluons by introducing the structure coupling constant, and then, of course, there is also the coupling, Yang-Mills coupling constant. So that amplitude actually is it is something up to now. It's a numerical constant, which I guess would be I, okay, which describes scattering of 3-point function, 1 gluon decaying to 2 gluons, if you wish, or something like that. Yes? Okay, cool. So now, just to convince you that this argument works, I just want to compute this amplitude. It's completely trivial to check that you get this amplitude by explicit computation of Feynman diagrams. Okay? I think that will be a good exercise. I didn't want to do it originally, but then I realized that may be a good thing to do. So, okay. So the only at the 3 level. Let's talk about 3 level. Yes, at the 3 level, you have just one diagram. Yes. All right. And you know, okay, you took although you took KFT course, you know that this vertex has 1 power of momentum, yes, because from derivative coupling, okay? And there are 3 polarization vectors which have to plug in for the 3 gluons. So essentially, you have a structure which you have 3 polarization vectors, okay, and 1 momentum. So the only thing that you can get is this type of objects, okay? So they always involve 1 scalar product of the polarization vectors, yes? All right, and then 1 of them contracted with some combination of momenta, okay? So now, so for example, this is a way, now I can show you, for example, if I take M plus the 3-point with the same helicity, I told you it must be 0, yes? Okay, how to see it? Well, if I choose the same reference vectors for all, so if all of them are plus, 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 okay, I can choose all reference spinors or vectors equal, okay? And then even for different momenta, like we have a P1 and P2, the scalar product will be 0, as you can see from here. Where you can see explicitly from this representation that essentially you are taking the only difference between the 2 polarization vectors will be this lambda bar spinor, yes? So then when you contract, of course, you'll contract 2 reference spinors, and that will give you 0, yes? All right? So that is, you see it like that. Now, what about the amplitude that, so let's talk about minus, minus, plus. Okay? For that case, I can do the following thing. I can choose a reference vector for 1 and 2, the same. Okay? And for the third one, choose, for example, P1. All right? And now I will repeat this computation. I will get what I need. But again, you see that the trick here, you see already where it is going, that choosing appropriate reference vectors simplifies computations, and this is known for like 30 or 40 years in QCD. Okay? So in this case, I cannot contract 1, 2. The only thing I can, so for example, where I can contract, you can ask where I contract, where I can contract 1. This, if you have the first one, I can contract with 2, but now I chose polarization vector same, so it's 0. I can contract also first with the third one, yes, epsilon, but then it will be 0, yes. So the only thing that I am left here is this object, and then I have, so I have these two are contracted, and then this is always, if you look at find my rules, that always involves difference of the momenta of the two other momenta. Okay. So now, if you plug it in, this representation, it will be 1, 2 square, 3, 4, believe me. Okay, by the way, this 3 will cancel because this is a 1, the reference, what I said. Third was 1. So 1 has a, well, whatever, yeah, okay, I'll just continue. And then multiplying simply by that, you will get indeed that it is 1, 2 cube divided by 2, 3, 3, 1. Yeah. All right? So I did reproduce this form. And now I see explicitly that from the Feynman diagram has also I, has also coupling constant, and has also the structure constant on A to A3. Okay? So this is telling you that we are really, this argument works, and then this argument works, and then again, it also, this computation illustrates that the appropriate choice of the polarization vector simplifies computations. But we won't be doing many computations of that type. All right? Okay.
And what about amplitude plus plus minus?
What?
What about plus plus minus?
You can do the same argument
Yeah.
by choosing them, and then you can repeat the same, exactly the same computation.
So it's not 0.
Yeah.
Okay.
Yeah. All right, cool. Well, you will get, okay, to be more precise, you will get that now the answer for plus plus minus will have the square brackets instead of the angle brackets, but for us this was all 0.
Oh, okay.
Okay, so for holomorphic, so I'm doing here the holomorphic solution. You cannot have both. Okay, fine. So what I want to do, just, I want to also, before I proceed further, I want to also focus now a little bit more on the color structure of amplitudes. It's something which is, again, very simple. Okay, it's here. Yeah. So now you have for gluons, of course, and I'm talking about non-abelian gauge theory. So for gluons, they are in the gender representation. So I can write it. Usually, I can represent it as n by for SU for n time by n times n matrix. Okay, where now these are generators in the fundamental representation, and now the generators satisfy, of course, the usual commutation relations. And so now the basic, then of course the amplitudes by itself, if you compute amplitudes involving many gluons, they will involve for each, they will have a structure constant, yes, and then, well, you have also, in addition to those diagrams, you have diagrams with 4-gluon coupling, and so on and so on. So each will come with some color factor, yes, which in this case is completely trivial for 3 points. But for 4 points, you have several possibilities. So in general, what you do, you can write, and it is just by looking in those diagrams, how they are built, you can show that if you have amplitude with several gauge bosons, with momenta p and helix n, and then gauge charges n, you can write them as you can factor out the color factors, which are traces in the fundamental representation, and actually there will be several color factors, and can show that all of them can be obtained by summing over all permutation of n-1 generators, which you permute these color indices. Now you permute indices from 2 to n by this permutation matrix. Okay, so together you have you have n-1 factorial possible. In this way, you write this amplitude in terms of n-1 factorial possible terms, times some factors which actually do not depend on gauge indices. And so they are essentially, there are some kinematical factors. Okay, like that, which, and these objects are called partial amplitudes, or color stripped amplitudes. All right? Okay, and these color stripped, these partial amplitudes are like really what is, when you make a computation in Yang-Mills theory, it's usually reported in terms of these partial amplitudes, which are coefficients of specific color factors, of group factors, okay? So to go back to this example that I had before, in this case, I told you that amplitude, I will now prove that the partial amplitude, now in this case you have two partial amplitudes. You have a -1 minus, 2 minus, and 3 plus. And I claim this is, well, I write it in this way. And then there will be another partial, there will be two, because I will have now two permutation of these two guys. And there will be then amplitude in which I have a 1 minus, 3 partial amplitude, which is this one. And this will be 2 to the 4th, by the 1, 3, 3, 2 to 1. Yeah, so we see that these are amplitude. When somebody tells you this is the amplitude, actually this amplitude is the smallest so-called MHV amplitude. MHV, you see, are amplitudes which have specific configuration of polarization, which I list in a moment. But for 3 points, there are such two partial amplitudes. And indeed, you see it as a trivial exercise to show that if I take this and take this trace 1, 2, 3, and then take this with the trace 1, 3, 2, you see that this guy has a minus sign compared to this one. Yes? Because, well, okay, this is the same thing. But if we interchange, you see here, there's a 3, 2, 1, 3. So this is the same thing, but there's also 2, 1, 2, 1, 1, 2, and 2, 1. So this is actually minus of that amplitude. So at the end, you will get a commutator of 2 and 3, which will be, you will use the commutation relation, and you have a trace with the remaining one, and this way we will obtain just the structure constant, right? So this is, yeah. So these are the partial amplitudes which you get for 3 points, and there are 2 of them, 2 factorial, yes? 2 of them. All right. Now, I won't be talking here about really not. I will not be talking how to compute. I will not explain how to compute these amplitudes and so on. But there's a class of amplitudes which are again very similar, which are called MHV amplitudes, for which the partial ones have very simple structure. Okay. So if you take amplitude, this partial amplitude, we can always choose the first. With partials, of course, a trace, so I can choose arbitrarily the first one. Yes. So I have this I minus, and then 2 plus, 3 plus, and j minus, and again all of them the rest plus. So this amplitude, which you have only 2 minuses, and the remaining are all plus. And then for that, the partial amplitude, up to again there is always an appropriate power of the coupling constant, but there is no color factor. So that this okay. So this is the n-gluon amplitude for a holistic configuration, which are 2 minuses and remaining pluses. And this one is actually holomorphic, which is natural extension of this minus amplitude for 3 gluons. All right. Now, how to compute it is another story. I mean,
What is the index of the last bracket?
The last bracket is ni. Sorry, yeah. You go like that.
Yeah.
Yeah. The last one is n1, I. Okay, so that's one example, explicit example of n-gluon amplitude. Is this MHV mostly plus amplitude. There are similar amplitude which are mostly minus MHV. They are written in terms of square brackets. It's exactly the same formula. All right? Now, to derive it is another story. As I mentioned, you can use these Scalist techniques. You can use some recursion relations, and you can use now to prove it. The quickest proof is using something which is called BCFW recursion relations, but I won't go into that. Okay? What I want to discuss now is something which is more related to celestial holography. I want to discuss now soft limits of amplitudes. Okay? Soft limits are the limits in which the photons or gluons have 0 momentum. Okay? That's what I'm going to do next. I won't be using partial amplitudes anymore. For that one, it's better to use full amplitudes. Okay. So let's talk actually about QED, and to make it even simpler, I can talk about scalar QED. Yes, all right. So there's a number of charged particles which are scattering. Now, I told you the moment the charge is somehow flowing like that, but always the momenta, which will be the momenta, will be flowing out from the diagram. So the diagrams like that, and so on. And you have photons emitted from all possible places, yes? I'm focusing here on the tree level, all right? So now, let's consider amplitudes which involve a photon with a momentum which goes to 0. So this is called soft photon. I will repeat later the same argument for soft gluon. Okay? Now, so here, and I've considered a theory of some, let's scalars, which actually are arbitrary masses, which have p square equal m square, for example, for this one, the on shell. And so now we see in such a diagram, the one thing that you have, here you have a propagator, 1 over p plus, okay, the momenta are always outgoing. So p plus k square minus m square, yes? So this is the same thing. Now, p square minus m square will cancel. P square will cancel m square. K square is 0 by itself, so the only thing we will get 2pk. Okay? So now you see that the momentum goes to 0. This diagram blows up. Divergence is coming from this virtual charged particle going on shell. Okay? And so we see the explicit here, where k goes to 0, it blows up. All right? So now, actually, well, we can see now what we can do actually is to consider the case in which you have some amplitude with some fixed number of charged particles, yes? By the way, in my conventions, all particles are outgoing. So that means that you have then the charge conservation condition, which tells you essentially like that, of course, the charge goes through, yes? But if you now count all of them as outgoing, then you have to change incoming, you have to do charge of the incoming ones. So the charge conservation is that the sum of all charges is equal to 0. Yes? If I take all momenta to be flowing out from the diagram. Okay? Okay. So now I consider, again, so I fixed some number of external momenta. So in other words, I consider amplitude in which have some number of particles with momenta p1 to pn, and just there can be also some photons here, okay, which are hard, yes, so I consider a limit in which one photon becomes soft, okay? So now I want to write explicit expression for this limit, and you see that the divergent part, these terms, appear only if the photon is coupled to external legs, yes? For example, if I have let me draw it like that, another scalar, anti-scalar pair. If I have a photon here, when momentum goes to 0, still this for other momenta fixed, this propagator is finite. Yes? So it doesn't blow up. So the only possibility, the only diagrams which blow up in the soft limits are the diagrams in which photons are emitted from the just external legs. All right? All right. So now, of course, what you get explicit depends on the theory. Now, I told you already that I want to consider is scalar electrodynamics. Then this coupling is completely trivial. Yes, so the coupling, if you have a particle of charge q, okay, which, this is a charge line, yes, but it's a charge q, and then you have a momenta, this is momentum p, this momentum, let's say p prime, and here's the photon, okay? Then the corresponding vertex is I times q, of course, is a charge coupling here, times, okay, there's index here, mu, p mu minus p prime mu, okay? Times the polarization vector, which is contracted with the polarization vector of the photon. All right? So that's what I get. This is scalar QED. The argument goes exactly the same way for real QED with electrons, yes, or with arbitrary charges. So that thing actually, because this is the polarization vector of, this is, okay, the polarization vector of the photon. So now you see that, of course, difference between p and p prime from momentum conservation plus k, while epsilon dot k is equal to 0. Yes, so that is simply equal to, then I can replace it by this one. Okay? And this is exact. This is always true. All right? So now, what I get from this diagram, I will get that from the propagator, and from the numerator, I get 2 times, then it will be I times Q, the charge, yes, and with 2 times the scalar product of the scalar product of the momentum of this particle with the polarization vector of the photon. Okay? And well, I can distinguish between now, I have, of course, the same thing happening all possible legs. So from each one, if I call it pi now, so now where I are all external momenta of all charged particles. So what I will get, that these, okay, so that will be the first thing which will appear here. Now this particle, now, since k is equal to 0, will have the same momentum, yes, as this one. So essentially what happens when the amplitude, which with this one soft photon, factorizes into the singular factor, times the amplitude in which there is no more photon, but this charged particle is exactly again on shell, has the same momentum, yes, because we assume now we have in the leading approximation k is equal to 0, yes? So what I get, that now I have this very simple soft, this most is like really the simplest possible soft theorem, that the amplitude with one soft photon is the sum of those, is the sum of amplitudes and sum of Feynman diagrams in which these photons are on external legs. And now what is left is just the amplitude without the photon. Okay? Now I'm summing here, of course, over soft factors, having also I, and it'll be Qi. Yes? Because one each, okay, which, where Q is this corresponding charge. All right? Is it clear? Okay. So this is again, so amplitude factorizes into this something which is called soft factor, okay, times the amplitude without the photon. It's the type of factorization theorem for soft singularities. Okay, now of course when k goes 0, this blows up. All right? Okay, so now what? Mm-hmm.
So how vector size is defined? So this is k attached to all. So this is sum of m, p1, p and k, where k can be attached to any of m.
Yeah, here I tell you there can be also hard. You can have a amplitude in which have some number of charged particles and some number of photons, which I leave them just as they are. They have some momenta. So that here is the charge. The sum is over all charged particles in the scattering process. Yes? It's sum over all, because in order to have the singularity, the photon has to emit it from the charged particle, This is QED, so it cannot be emitted, of course, for the photon.
So, no,
I'm doing abelian case. It's the simplest possible case.
left-hand side, it's not just one diagram, but some all.
Yeah. So in other words, if you have you're asking, you have amplitude in which you have like okay, like that. Yes, and you have some number of charged particles. Okay, and then some number of hard photons. This is formula which applies to the case when there's one of those guys, one of photons becomes soft.
We don't know exactly where.
Yeah, yeah. So then I told you I have to include that is the singularity is coming from the diagrams in which this photon is attached to external legs, not the inside, because you see here when it's inside, then this is finite. All right.
And if you want more to include more soft photons, then we apply this formula for each soft photon again.
Yeah.
And again,
Then there are interesting questions. For example, what happens if you take the limit of one photon first and then the second one and reverse the order? There are lots of interesting questions that you can ask.
And what are the subleading terms?
Oh, that's exactly that will be the next thing. First thing, I want to go through soft theorems and the leading up. That is really leading. I don't care here. For example, I made a statement that this momentum now, when k goes to 0, is exactly pi, yes? But actually, this momentum is pi plus k. So one source of subleading terms will be actually expanding this amplitude in this way, and this way I would generate one class of subleading terms. It is surprising that you would say, well, in subleading terms, these terms you see when I now parameterize explicitly k in terms of energy and so on, they go 1 over the energy of the photon, okay? These are finite in the limit when energy goes to 0. But surprisingly, what I will show, and this is so-called Low's theorem, that we can tell also, we can all beyond the leading order singularities, and these diagrams, we have some information from these diagrams in which photons are emitted from internal lines. That seems very strange, but this is what happens. That's Low's theorem. Okay, so we'll have actually in QED, we know explicitly that the leading singularities, infrared singularities, which I will write explicitly what leading is, okay, and subleading factorize in this way. So I can write essentially everything in terms of some factors and some amplitudes without the photon, like that one. The subleading theorem will involve some derivatives of the amplitude in the absence of photons. Okay? Okay, good. So let me write down now what this is how Low, Francis Low.
Can I ask, is this factorization some universal feature of soft? If we were to consider not those theories, would they?
Well, no, I will tell you what happens. This is true for scalars or for fermions. Actually, Low's theorem originally, of course, who cared about scalars, yes? So it was for electrons, yes, for different electrons with different charges. That's an obvious thing to do, okay? And then well, you see the similar theorems hold for what I will explain. The similar theorems, factorization theorems of some singularities, hold for in Yang-Mills theory and also hold in Einstein's gravity. And I will try to write them in such a way as to make connection with celestial holography. Okay? So that's the whole point, because as you see from Sabrina's infrared triangle, yes, relation between soft theorems, yes, and word identities or symmetries of celestial sphere. All right? So now I want to, so the thing which, these are very well-known things, but what I want to write them in terms of, I want to write everything now in this Helician notation, and this notation which I use is complex variable z, which is this projective coordinate of the momentum spinor. All right? Okay, so we'll need that. Okay, so Yeah. So that thing, by the way, this is momentum k, this is momentum pi. So this is exactly I want to use now this formula here. Let me choose just positive. Let me choose just to illustrate, use the do this theorem for positive holistic gluon. Then this factor up to this factor of I is sum of the charges. And then now I have that thing, which is the 1 over the square root of 2. There will be R. Now the momentum, well, I will call this PIP, yes, for each of them. P or PI, or I, yes, and IK, which you have from here, yes, P is I, okay, and then I will have this reference vector RK from here, and then I will have this K times PI. So this is, you remember that 2K times PI is IK, KI. Or better, I write a KI, IK, KI. So I have here IK, KI, yes. This thing cancels, yes. And I guess something which is interesting, which is purely holomorphic, yes? Well, by the way, the square root of 2, what this 2 will do, will move this sum over I, there will be QI, and then there will be square root of 2, which will appear in the numerator, yes? And then so that thing is, again, once again, square root of 2, sum over QI is purely holomorphic soft factor. Okay? Now, the one thing which I should mention already here, or at that level, because now you see I'm using, again, in this, when I write it like that, I use a specific reference vector, yes? But the end result should be independent of the reference vector for the polarization vectors, yes? Because the whole thing is gauge invariant. Yes? So the whole thing.
What is the spinor I?
I is I, okay. I is pi or lambda pi. Okay. The momentum splitter associated momentum pi. So when I was writing before, always, I think I mentioned before, the notation was, for example, 1, 2 was the same thing as a lambda 1 alpha, lambda 2 alpha. What? Null. Yeah. Okay, fine. Yeah. So, yeah. When I write it like that, I write it for, yeah. In this case, it's, yeah, I specified the case of massless scalar. That's true. That's true. Yeah, I should have mentioned that. Okay, but the whole thing goes through for massive scalars as well. But the thing is that now it gets written in a very nice way, in this way. And now, so what I want to do, I told you that the spinor I, okay, was Zi, 1 here, and some factor which here I call it, I can call it now like T, yes? Okay, so that thing is equal, that thing, I'll write in a moment, but before I sort of got sidetracked, because the thing that I wanted to mention, that I mentioned this dependent of the reference vector, and I told you that the whole thing that's dependent should disappear because the result is gauge invariant. To see that gauge invariant, I can, what I do, I replace the polarization vector by the momentum. Then this, if I replace polarization vector by the momentum, then I get simply sum of the whole charges. But I told you, from charge conservation, they add up to 0. So you see explicitly that the soft factor is gauge invariant. Okay? So now, and then it's completely, then it is, I could write actually this, okay, so this is square root of t. Now, by the way, of course, these overall factors of, for the, these overall factors will cancel for the momentum pi, so that all, at the end of the day, we are using this parameterization, that thing is square root 2 sum of qi. There will be 1 over, for the momentum, there are two, for two, there will be 1 over omega, where the omega is 1, and then we z, from here has zr minus zi, divided by zr minus zk, times, I'm having zk minus zi, yes? Zi. By the way, when you have this, when you have a difference of 1, let's say of I and j, that this always will be called zij. So this is something which I call zri divided by zrk, zki. Okay? All right. So you see that, so you see at the end that you have explicit, and omega, on the other, omega is the energy of the photon. Yes, as I said. So when energy of the photon goes to 0, this is the soft factor. And this is 1 over omega, 1 over energy singularity. And now, times something which seems to depend on the reference vector. But it doesn't. The reason is that zri, zrk plus zki, all right? So that means that the subfactor is square root of 2, sum over, there's a qi, yes, sum over qi. Okay, 1 over omega, sum over qi, 1 over z rk, plus 1 over zki. Okay? And now you see that when I sum over, so that thing does not depend on I. So again, by charge conservation, this goes to 0, and we obtain very simple soft theorem for the soft factor. It's 1 over omega of the square root of 2, sum over qi divided by zki. Okay? Where k is, of course, the k is the z of the, same thing for k, of course, k has a zk 1 times square root of omega. All right? So this is the soft theorem. This is the explicit soft factors, which you see, where you really see that it is a very simple thing. It just appears as a factor for the amplitude without the photon. And it again has this soft singularity, which goes like 1 over the energy, and then has this factor which depends only on this projective of this coordinates z, which at the end will be identified with and at some point, Sabrina will talk about celestial amplitudes in which these z's, which appear here in this context as these projective variables, they will correspond to the positions at which you insert operators in celestial conformal field theory. So then you have these, actually then, if you realize that, then this whole soft theorems looks like type of word identity in two-dimensional celestial conformal field theory, because you have these simple poles, yes, which appear from OPs of operators. Right? So that's where the connection comes in. Okay. So that was done for for the scalars. I'll do a similar theorem. It looks more interesting for Young-Mills. Okay, so let me do it now. It will look a slightly different. Okay, it looks slightly different. So, but again, the idea is exactly the same. Now we have some number of external gluons which are hard, and some diagrams which connect all of them. And then, like for example, here you have I call it PJ. Yes, in this case, it's like momentum of some gluon, and then the momentum of the soft gluon will be K, and let's assume there's a color index C. Okay, and let's assume that that one has color index Cj. So again, the singularities will come from the poles which appear when K goes to 0. This intermediate virtual gluon goes on shell, and you get singularity which from that propagator 1/2 Pj times K. Okay? It's exactly the same story. The difference is now that this is non-abelian coupling. So actually we have a fixed color index. If you have fixed color index of this hard gluon and fixed color index of the soft gluon, you can, the coupling involves actually all possible ones which are related, intermediate one contain all possible colors related to them, all ones which appear in the corresponding structure constants. Okay? All right. So, and again, it's the same thing. This gluon with momentum K and color index C can be attached. The only place where it can, the only diagrams in which give rise to those singular factors are the ones in which this soft gluon is attached to external legs. Okay, that's obvious. And then, so the only thing so I want to focus on one specific one, and then, so the only thing which to determine actually to figure out what is the structure of singularity is to just to write explicitly this vertex as I did before, yes? And that is very simple. Here in this vertex, apart from the coupling constant, yes, there is a structure constant, CCJA, yes, CCJA. And then there is well, there's now I'm doing it. First of all, there's minus I, now I write explicitly, divided by 2K Pj, which is from the propagator. Okay, there is structure constant from the vertex, and then I have to write there's a minus I from the vertex, there's a minus G. Okay, and then there is now there is a three-gluon coupling, so it's a little bit more complicated. But I told you before, it contains all terms in which the two. Okay, if this is again, there's another index which is index of. I have talked to about the index of. Okay, this index here. Yes, which is the index of the vector index of the which connects with the rest of the diagram. Then there is the K minus P J mu. Yes, so that two polarization vectors contract in this one, and now what is left the momentum factor, and there will be another one. And this one. There is always two polarization vectors of that one or of that one, of the soft photon and of the hard of the soft gluon and of the soft of the hard and of the soft gluon. Yeah, there are three terms. This is just you look at a textbook and you see what is the three gluon vertex, and you plug it in, and this is what this mu index will couple then to the rest of the diagram from Feynman rules. Yes. Okay, so now you see that, again, what we can do is the following thing. For the first term, okay, suppose that now I also have to specify the polarization of this hard gluon, so it's AJ, okay, and I have to specify the polarization of I have to specify polarization of the soft photon, and now you see that one thing that okay. First of all, this term is already of order k. Got rid of it. This term is like, and when k goes to 0, then this pj mu couples to, then the momentum of that intermediate gluon becomes pj. So then I'm contracting this momentum of the gluon with the rest of the diagram that will give you 0. So this goes away. Okay? Then this term is of order k. So the only term which I get is this one. Okay? So we see that actually what is happening, what is contracted with the rest of what is contracted with the remaining part of the diagram is the polarization vector of this hard gluon. All right? And there's this soft factor, which is, and then what is left here is the scalar product, okay, and then this is the scalar product of polarization vector of the gluon times the momentum. So that thing, at the end of the day, we can write it the following way. That we sum over all possible external legs, yes, which involve now hard particles. And then we have this, well, there will be this, from here, I will have the scalar products of the polarization vector with the momentum, okay, and then the propagator. And then I will have a CJA from the color factor. And then what I will have here is the amplitude in which I have, this is the contribution coming from the diagram in which J emits the soft gluon. So now I will sum over all possible, all possibilities. So then, for example, in this case, the J index, as you see from here, is replaced by, essentially, this is replaced by A. So the PJHJA instead of CJ. Normally, that would be CJ. But now this index appears here. And then PN, HN, CN. Okay? So, yeah. So this is the soft theorem. It's a little bit different because now the soft emissions also involve colors. Yes, involves this all possible structure constants, which involve the color charge of the original of the soft guy, and involve also the color charges of the guys which are emitting it. Okay, so this is what you get. Okay? All right. You're almost done. Yeah, I think like 5 more minutes. I can write it down now, and I can write the whole thing, repeat the whole thing in Helicity notation. So the thing this amplitude in volume 1 soft gluon is square root of 2 divided omega sum over J F C C J A. Yes, and now I will get again 1 over, I told you, Z Rk, where R is the reference of the polarization vector, plus 1 over Zkj times the amplitude in which now the J1 was replaced by P1, H1, and C1. And then here I have a H, the J1 has the helicity like that, and then has the same, has the J1 is now has the helicity of the S, the original helicity. The only thing which is affected is the color index. Okay? And I get now, so the only difference now is that this index A appears, this index, which appears in the soft factor, appears in all possible places, corresponding to all possible emissions from all possible external legs. All right? So now, and as before, I have two. I did the trick as before, splitting the soft factor into something which does not depend on this on J and the rest. So this is it. And now here I have a term which a priori can depend on the reference vector. Yes? Okay.
What is the letter just before the bracket?
What?
What is the letter after the structure constant? After just next to the structure constant.
Next to the structure constant, one of ZRK,
Okay, and there is no
ZKJ. This is the one which is K.
Okay, this is okay. Outside of the bracket there.
Here,
Yes.
there's nothing more. The structure constant, and there's one over the amplitude. Yeah, that was the leftover from the last blackboard. Yeah. All right. So now, but the result should not depend on the reference vector. Yes. So how come? There is this what you have here. So in other words, in order to prove that the result is simply that I can cross it out, is I have to prove that this object, which is sum over J over all gluons, Cj for arbitrary C, which is the color index of the soft gluon, well, now the helicity, but what matters here is this has to be 0 in order for this thing that to not depend on the reference vector, which is to be gauge invariant. This is indeed 0. What is this? Is the global word identity of color symmetry. Okay, how to get it? How to prove it? Okay. What you do? This argument is complete. Does not depend on the momentum helicity. This is a property which deals only with color factors. So we know that when you have a amplitude, scattering amplitude for n gluons, you have creation operators, yes, and annihilation operators. Here we can take all creation operators, which some indexes which are C1 up to C. And yes, for n gluon amplitude. That is essentially the amplitude. You take matrix element. Well, there's the same number of A and E daggers. Yes. So okay, but yeah, in order for that to be non-zero, yes, because that would be 0, strictly speaking. Yes. So there are some of them which are creation, some of them are annihilation. Yes. So this is a starting point for computing a scattering amplitude. So what you do? Use the fact that when you act with some colored charge on the vacuum, you will get 0, yes? Also, if you act on this side, yes, you will get 0. So together, you construct the following object, which is the commutator of a specific colored charge, global charge, and this chain of creation and annihilation operators. Yes? And that has to be 0 because vacuum has 0 color charge. Yes? So now, of course, for that you can use, it's called, I think, called Leibniz rule. So that the sum, so this thing, the commutator of the charge operator with a chain of other operators is the sum of, the sum of those ones in which, of terms in which this charge rotates individual, like say this case, some A dagger, Cj, yes? And then everything else here is unchanged, yes? But acting on a creation annihilator, creation annihilation operator, this commutator performs rotation. So this is equal to F, C up to a sign, and I, A. Now, well, okay, dagger, okay, this is the same indexes, yes, which I called before A. So you see that this is indeed the sum. What this is, this object is the sum of those amplitudes in which all possible creation and annihilation operators are rotated by global gauge transformation. All right? So this is indeed 0. So the soft theorem now, as you see here, I can write in the following way. Okay? It's involved just the simple, there's a 1 over omega, which is 1 over the energy of the photon, and then the structure constants, and there's again a single pole when this position, the coordinate z of the photon, this pole, which appears when the position of the photon on celestial sphere overlaps with the position of one of the external gluons, which are hard. Okay? All right, so this essentially, again, so this is Young-Mills. You can go through similar argument for gravity, because gravity is essentially a square, okay, and that level, at that level for Feynman diagrams, gravity is a square of Young-Mills, which means that the polarization vector of spin 2 are the polarization, are the products of the polarization vectors of spin 1. In addition, that is a well-known result, which is for, I think, 30 or 40 years, that amplitudes, which involve a number of external gravitons, now, can be written as some type of products, in quotation mark, of the Young-Mills amplitudes. Now, when I write it like that, of course, well, there are no color factor series, but this object will enter in these relations between graviton scattering and gluon scattering. The KLT relation involve partial amplitudes, yes, from which there are no color indices. So this makes sense. Yes. So essentially, a given gluon amplitude, let's say for 4 gluons, can be written as products of some partial amplitudes from Young-Mills multiplied by some kinematical factors. Okay? And by using that fact, you can also prove that there's a leading singularity, soft singularity in gravity, which goes like 1 over the energy of the soft graviton in this case, okay, which has exactly the same form. Okay? All right. That's all for today. Questions? More questions?
So, comparing this with Sabrina lecture yesterday, why, when I consider electromagnetic field on sky, and I'm just classical relativist, I should care about this soft stuff. I I just have electromagnetic field on scry. I don't have any Feynman diagrams, but suddenly
Okay, so for that, I think you have to wait. Yeah, I know. Yeah, you see that the point is that I already mentioned that, I would have to go, I don't know if, I would have to take step from these amplitudes to celestial amplitudes, okay? The celestial amplitudes are obtained from this type of momentum amplitude by Mellin transform with respect to energies, okay? And that actually, the Mellin variable dual to the energy becomes the dimension of the operator, okay? Now, this is how we're left. So essentially what you see that the soft theorem corresponds to some relation between celestial amplitudes which actually correspond to two-dimensional word identities of two-dimensional conformal field theory. The Z's are coming from the OP product. For example, if you have Vesumino current, where you have any charge, okay, take any charge operator, what it performs the gauge rotation, which means that a OP contains a single pole, okay? And the single pole is responsible, again, the word identities which in two-dimensional CFT involve some of this type of terms, where this Z's are coming from OPs, from the currents with operators. That's the connection, roughly. So you have to go to the next step, and you go to celestial amplitudes, where really these momentum amplitudes, which I'm discussing now, are being transformed into some two-dimensional CFT correlators. And then the only thing which happens here is essentially that you integrate out the energies and sort of convert this dependence on the energy into the dependence on the dimension. So when dimension of some operators, in this case will be dimension 1, this soft photon, be associated with dimension 1, which is exactly what is Vesumino current, then you will get this type of identity between celestial amplitudes, which correspond to the CFT correlator, which will insert Vesumino current. And this is a word identity. So then these, you ask what are these currents doing on celestial sphere and performance, and then you can really make a connection connection with celestial sphere. Yeah.
Perhaps another way perhaps of asking this question perhaps is, how should we think of these divergences which are appearing in the S matrix? Is it some sort of natural physical property, or is it a sign that the naive way of defining the S matrix is?
Could you repeat louder?
Yeah, I mean, these divergences which we see in the soft poles, should we think of them as being some natural physical stuff, or is it a sign that the naive S matrix is ill-defined? How should we think of it?
Okay. Well, the question of ill-defined is a matter of I think that is poles. Yes, but and when you do the celestial amplitudes, then these poles appear only for some special dimensions of operators. So instead, the photon now corresponds to such operator which has dimension 1. So you have a 1 over you have type of singularities which appear when the soft singularities now translated into singularities in the dimension of the operator. Okay, so yeah, so it depends how you look at it. From the point of CFT, it's nothing unusual, but from the point of view from the point of view of S matrix, yes, that's true. It's a singularity. Now, I will mention maybe later or tomorrow that this and how we handle it in elementary particle physics is that we ignore that type of a problem and we define by using the fact that actually we cannot catch a zero momentum photon because you cannot build a detector. Yeah? And then, that's how we do it. And then that means that we combine this type of amplitudes, which are trivial amplitudes, with loops. And then there are theorems, which tells you that if you consider physical observables, which take into account this energy resolution of our detectors, these amplitudes are finite, at least in QED. For QCD, it was never proven. Okay, but that's what we do. So that singularity, yes, that's true. Strictly, you say, well, from the very beginning, if you talk to axiomatic field theory, there's no scattering amplitude in Q, and they'll tell you it's an ill-defined object in QED because of that reason. Yeah.
But can I add more question to this?
Yeah.
This is infrared singularity, right?
Yeah.
And loops will be UV singularity.
Yeah, they will have, yeah.
So and they will cancel each other.
No. It's completely different. Ultraviolet singularities are sort of legal. Yes, you remove them by a randomization process. Actually, for the
That would understand what you said, that loops will somehow help us with
what? The loop?
I just understood that loops will help us with this type of.
Exactly. So loops, in order to proceed as I described now, use block-logic theorem, you have to add loops. Mm-hmm. Now the loops, of course, and when you have loops, of course, you have ultraviolet divergences. Actually, what is very special, that only 4 dimensions, what is very special and what is actually, well, I know we'll talk later, that what makes celestial holography very special is that it works very well in 4 dimensions. That you can define it like CCFT, which is 2 dimensions, CFT in 4 dimensions. And 4 dimensions are very special. I think that may be the reason why we live in 4 dimensions. 4 dimensions is the critical number of dimensions. We have both ultraviolet and infrared. If you go to 5 dimensions, the loops will not have infrared divergences. Yes, they will have ultraviolet divergences. If you go below 4, you won't have ultraviolet divergences, but you have a more than logarithm, you have a very bad infrared divergences. So 4 dimensions are very special, and I think that celestial holography somehow builds on that, okay, on this very special value. I wouldn't say that this is the reason why we live in 4 dimension other than 5 or 3 or 11, if you wish, yes. But yeah, but that's very special. Yeah. All right, okay.